Picture a perfectly straight line cutting across thousands of light-years of space, a trail of brand new glowing stars stretching further than the human mind can easily grasp. When astronomers first stumbled upon it, they were completely stumped. Nothing in the catalog of known cosmic phenomena seemed to explain it. But when they trained their telescopes on the very front of that streak, everything snapped into focus, and what they found was somehow even stranger than the stars themselves. Leading the charge, like the tip of a cosmic arrow, was a supermassive black hole, racing through space at nearly 1,000 kilometers per second, and behind it, like exhaust fumes from the most powerful engine imaginable, stretched millions of newborn stars. Now hold on a second. Black holes destroying stars, that we've heard of, that's practically their reputation. So how on Earth, or rather how in the universe, is one creating stars? And maybe even more puzzling, where did it come from? What kind of event could possibly fling a supermassive black hole through the cosmos like a bullet fired from a gun? These are exactly the questions we're going to dig into today, as we unravel one of the most spectacular and bizarre discoveries in modern astronomy, a runaway black hole, leaving a glittering trail of stellar nurseries in its wake. We're going to figure out why this so-called destructive cosmic monster is behaving more like a cosmic gardener, and we're going to look at just how common, or how rare, this kind of thing might actually be. To tell this story properly, we have to start with the telescope that kicked it all off, the Hubble Space Telescope. Hubble has been one of humanity's greatest windows to the universe for decades now. We've used it to study star-forming regions called starbursts, to examine black holes, to photograph breathtaking nebulae, those vast clouds of gas and dust that glow like cosmic watercolors, and to peer into the hearts of distant galaxies. In fact, exploring other galaxies is one of Hubble's real superpowers. So in 2023, a team of Hubble scientists led by Yale University astronomer Peter Van Dokkum was doing exactly that, scanning the neighborhood of a nearby dwarf galaxy when they noticed something deeply strange. There it was, an oddly, almost suspiciously straight line of young blue stars and gas, cutting across space like a ruled line drawn by some cosmic hand. This streak stretched nearly 200,000 light-years. That's almost twice the length of our entire Milky Way galaxy. And it wasn't just long, it was massive, containing the equivalent mass of roughly 100 million suns. Spectacular barely covers it. Peter Van Dokkum himself, upon making the discovery, said, and I'm quoting directly here, "Something like this has never been seen anywhere in the universe." That's not a phrase scientists use lightly. When an astronomer of that caliber says they've never seen anything like it anywhere in the observable universe, you know you're dealing with something genuinely extraordinary. The team immediately got to work, trying to puzzle out what this streak could possibly be. They came up with several candidate explanations. Could it be a super thin galaxy, oriented perfectly edge-on to us, so we were only seeing it from the side, like looking at a dinner plate from across the room? Maybe it was a runaway black hole. Or perhaps this was a case of what scientists call jet-induced star formation, where powerful beams of energy blast through interstellar gas and trigger stars to form along the way. To narrow things down, they needed more data, and fortunately, that was on its way. Follow-up observations from the W.M. Keck Observatory in Hawaii added a crucial piece of the puzzle. The oldest part of the streak appeared to connect back to a dense, actively star-forming galaxy located about 7.7 billion light-years from Earth. 7.7 billion light-years. To put that in perspective, that's more than halfway across the observable universe. The streak itself measured nearly 200,000 light-years from end to end. But these new details only deepened the mystery. Where did this long, thin band of stars actually come from? And why did it seem to be forming specifically in the wake of some kind of massive, fast-moving object at its tip? Let's go through the explanations one by one because the process of elimination here is genuinely fascinating. First hypothesis: a super-thin, edge-on galaxy with no central bulge, what astronomers call a bulgeless galaxy, oriented so that we're seeing it exactly side-on. It sounds plausible at first, but there was a problem. The stars in this streak weren't the mixed bag of ages and colors you'd expect from a real galaxy. In a typical galaxy, you get everything from ancient red giants to young blue stars, a whole spectrum of stellar life stages. But this streak? Every star in it was young and blue. That's a major red flag. Galaxies don't work that way. And there was another clue that really sealed the deal. The tip of this streak, the very front of the line, gave off an incredibly bright signal in a specific wavelength associated with doubly ionized oxygen. In scientific notation, this is written as O3 in brackets, but what it means in plain language is this. 2 electrons had been stripped away from every oxygen atom at that location. To do that, you need an enormous amount of energy. We're talking about extreme environments, the kinds of conditions you'd find blasting out from a quasar or at the shock wave of a violent cosmic event. Yes, galaxies can be energetic, but to produce that kind of signal concentrated specifically at one end of the feature, the odds of that happening in a normal galaxy are vanishingly small. So the narrow edge-on galaxy idea? Ruled out. Second hypothesis, jet-induced star formation. Now this one had some genuine precedent behind it. We've actually observed radio jets triggering star formation elsewhere in the universe. There's a famous example called Minkowski's object, a peculiar little star-forming system found near a galaxy designated NGC 541, where a radio jet from the neighboring galaxy appears to have sparked a burst of star formation. We've seen something similar happening in Centaurus A, one of the closest active galaxies to us. So the idea isn't crazy. A powerful jet from the nearby galaxy could theoretically ram into interstellar gas along its path, compress that gas to higher densities, and trigger new stars to ignite along the jet's trajectory. That would give you a line of stars. But here's where the geometry kills the theory. Think of a jet like a garden hose. It's widest at the nozzle, and the spray spreads outward as it travels. The furthest point from the source would be the broadest and most diffuse part of the jet. But this streak is the exact opposite. It's narrowest at the tip, the point furthest from the nearby galaxy. That's completely backward for a jet. On top of that, a jet's most powerful interactions with surrounding gas would happen closest to its source, right next to the galaxy that launched it. But again, this feature shows the opposite behavior, with the most intense activity at the far end. The shape, the intensity pattern, nothing matched the jet model. Ruled out. With those explanations off the table, the team found themselves gravitating, no pun intended, toward the more extreme, more exotic possibility. Could this really be a runaway black hole? The idea of a runaway black hole has actually been floating around in theoretical physics for decades. Back in 1983, physicist Michael Fitchett showed mathematically that when 2 black holes merge, the resulting gravitational waves they emit don't necessarily cancel out symmetrically. If those waves are stronger in one direction than another, a phenomenon called asymmetric gravitational wave emission, then the merged black hole experiences what's called a gravitational recoil, like the kickback from a rifle. And depending on the mass and spin of the original black holes, that recoil can be powerful enough to send the newly merged black hole rocketing off in one direction at extraordinary speed. The math said it was possible, but for a long time, nobody had ever actually seen one. Astronomers knew it would be incredibly difficult to detect, unless, of course, the runaway black hole happened to leave behind some kind of dramatic, visible signature as it traveled, which, as it turns out, is exactly what seems to have happened here. The hunt for a definitive answer took another major leap forward a few years after the initial discovery. In December of 2025, Van Dockum once again assembled a team of astrophysicists, this time armed with humanity's newest and most powerful space observatory, the James Webb Space Telescope. With its dramatically improved resolution and sensitivity compared to Hubble, the team was able to examine this bizarre feature in far greater detail than ever before. And what they found helped confirm what the evidence had been pointing toward all along. One of the most critical pieces of evidence that the James Webb Space Telescope was able to confirm. So what exactly were astronomers looking at? At one end of this long, thin line of stars, there was an absolutely enormous bow shock. Now, think about what happens when a supersonic jet tears through the air. The air gets violently compressed in front of it. Or picture a speedboat cutting through water, pushing a wake behind it. Something was doing exactly that to the interstellar medium. the gas and dust that fills the space between stars. Something was plowing through it, hard and fast. Obviously, nobody thought this was a plane or a boat. The team's best explanation for what could create a bow shock on this scale was something almost unimaginably massive, a supermassive black hole, at least 10 million times the mass of our Sun, barreling through space at roughly 1,000 kilometers per second. At that speed, it would be compressing and heating the gas ahead of it like a cosmic battering ram. But of course, they still had to prove it, and the evidence started stacking up. The team measured strong emission lines, essentially specific colors of light that certain excited gases give off, that confirmed the gas right at the very tip of the structure had been heated and compressed by a powerful shock. On top of that, they detected a sudden jump in gas velocity. In other words, the gas wasn't just moving a little faster, it was moving supersonically. Something was pushing through that gas at speeds that broke the local sound barrier in space. All of this evidence pointed toward one unavoidable conclusion. The entire glowing structure, that 200,000 light-year-long streak of stars and gas, was the wake of something enormous. And the only object in the universe that could be both massive enough and compact enough to produce this kind of effect is a runaway supermassive black hole. So with that, the team had done something extraordinary. They had confirmed the very first photographic evidence of a runaway supermassive black hole. And they gave it a name, a straightforward, no-nonsense name, Runaway Black Hole One, or as it's abbreviated, Runaway Black Hole One. Now here's where things get genuinely surprising, because there's a question that's probably already forming in your mind. We typically think of black holes as destroyers. They capture nearby stars, solar systems, even light itself. They devour everything in their path. So how on Earth, or rather, how in space, is this black hole creating stars? Here's the thing. As Runaway Black Hole One carves its chaotic path through the cosmos, that powerful bow shock is doing something unexpected. It's compressing gas ahead of and along its trail. And as that compressed gas gradually cools down and mixes with surrounding material, clumps of it become dense enough to collapse under their own gravity. And that's exactly how new stars are born. So the very chaos and violence of this runaway black hole is actually seeding the distant universe with the conditions needed for star formation. From cosmic carnage comes stellar rebirth. It's honestly one of the most poetic things in modern astronomy. But that naturally raises the next big question. Why is Runaway Black Hole One hurtling through intergalactic space at breakneck speed in the first place? Where did it even come from? Fortunately, this part of the mystery came with its own built-in trail of evidence, literally. The team, led by astronomer Peter van Dokkum, noted that with the black hole's current velocity of about 954 kilometers per second, the evidence is, and I'm quoting here, very strong, bordering on overwhelming, that this is indeed a runaway supermassive black hole that was ejected from its original host galaxy. It was flung outward with enough force to escape not just the galaxy itself, but also the circumgalactic medium. That's the faint, diffuse halo of gas that extends around a galaxy like a thin atmosphere. And when you follow that long stellar trail backward, like following a road on a map, it leads directly back to the source. It points straight to a galaxy system that astronomers have nicknamed the Cosmic Owl. This two-galaxy system sits somewhere between 7.5 and 9 billion light-years away from us. It earned its nickname because, well, it genuinely looks like an owl. Two bright eye-like regions and a beak-like structure connecting them. And this unusual little system holds the key to understanding what launched Runaway Black Hole One on its wild journey. The Cosmic Owl's bizarre shape was created through one of the rarest events in the entire universe, the collision of two ring galaxies. Now, ring galaxies are already exceptionally rare. They make up just 0.01% of all galaxies we've discovered so far. Only a few hundred are known to exist in the part of the universe we can observe. And why are they so rare? Because forming a ring galaxy requires one galaxy to pass almost perfectly through the center of another galaxy. Think of it like playing darts. The chances of hitting the bullseye are far lower than landing anywhere else on the board, no matter how steady your hand is. And galaxies, unlike dart players, don't get to practice their aim. So one-ring galaxy forming is already a rare event. Two-ring galaxies existing close enough to each other to interact, even rarer. And two-ring galaxies actually colliding with each other? That is so improbable that you can immediately understand why the cosmic owl, also nicknamed the infinity galaxy, is considered an exceptionally rare type of galaxy merger. It's essentially a cosmic lottery jackpot, won twice in a row. Astronomers say that the beautiful symmetry of the resulting cosmic owl structure is a strong indicator that this was a head-on collision between two galaxies of roughly similar mass. Both of those ring galaxies are relatively small, each one only about a quarter of the diameter of our own Milky Way. At the time of the collision, each of what we now see as the owl's eyes represented the galactic core of one of these ring galaxies, densely packed regions of older stars, each surrounding their own supermassive black hole. And then there's the beak, that region where the edges of the two galaxies began to overlap and merge around 38 million years ago. The beak is a place of active collision, packed densely with molecular gas, essentially the raw fuel for star formation. And this ancient violent collision may have been the very trigger that sent Runaway Black Hole One screaming away from its home galaxy at nearly 1,000 kilometers per second. So how did it actually escape? There are two leading explanations that astronomers have considered. The first is a merger between two black holes. The second is a three-body gravitational interaction involving a third black hole. Let's walk through both. When galaxies collide, their supermassive black holes don't just stay still. They get drawn toward each other by their immense gravity, slowly spiraling inward. When this discovery was first revealed back in 2023, before follow-up observations from the James Webb Space Telescope had confirmed it, the leading explanation seemed to be the three-body scenario. The idea was that the galactic merger brought three supermassive black holes close enough together to gravitationally interact. In this picture, the two black holes at the cores of the merging ring galaxies spiral together and form what's called a binary black hole system, two black holes locked in orbit around each other. This kind of binary system can persist for billions of years, but if a third supermassive black hole wanders close enough to that gravitational tug-of-war, the interaction can violently catapult one of the three black holes outward with enough velocity to escape the galaxy entirely. It's essentially a gravitational slingshot on the grandest possible scale. But with more accurate measurements, the picture shifted. The better-fitting scenario turned out to be the black hole merger explanation. And the key piece of evidence, the smoking gun, was the mass. If three black holes had been interacting, the physics tells us that the lightest one would most likely be the one kicked out of the system. But in a merger scenario, it's the newly combined, larger black hole that gets ejected. And Runaway Black Hole One was calculated to have a mass greater than 10 million times the mass of our Sun. That's far too massive to be a small, lightweight third black hole getting booted out. But it's exactly what you'd expect from a binary merger followed by a gravitational kick. Here's what that would have looked like. As the two ring galaxies of the cosmic owl collided, the supermassive black holes at their respective cores spiraled together and eventually merged into one brand new combined supermassive black hole. When two black holes merge, they release gravitational waves, ripples in the fabric of space-time. And if those gravitational waves are released asymmetrically, more strongly in one direction than another, the resulting recoil can be absolutely violent. Violent enough, in this case, to send the newly formed black hole rocketing out of the host galaxy entirely. The models built around this merger scenario are consistent with the measured velocity of Runaway Black Hole One and with the mass of the galaxy it left behind. In science, that kind of consistency between theory, simulation, and real-world measurements is about as close to confirmation as you can get. And so, what we're left with is a genuinely staggering picture. A supermassive black hole that was literally hurled out of its home galaxy by the sheer force of gravitational wave recoil. In the aftermath of a merger like this, the entire galaxy system may have been temporarily left without any central black hole at all. No anchor, no gravitational heart at the center, just an enormous galaxy with a gaping absence where its most massive object used to be. Now, to be fair, we don't yet have concrete evidence to confirm that one way or the other, but the possibility alone is mind-bending. What we do know is this: that unusual galactic merger sent a supermassive black hole racing toward intergalactic space, and the confirmation of Runaway Black Hole One, the object at the center of this whole story, marks a genuinely new era in our understanding of how supermassive black holes, galaxy mergers, and star formation are all connected. This is the first clear observational confirmation that supermassive black holes can actually be slingshot out of their host galaxies. And not only that, it revealed something nobody quite expected: a stunning trail of newborn stars left behind in the black hole's wake. Like the contrail of a jet cutting across the sky, except instead of water vapor, its entire stellar nurseries strung out across space. Before this observation, computer simulations had predicted that the wake of a runaway black hole might glow, that the compressed gas in front of it would light up somehow. But very few researchers expected that wake to become a place where new stars are actively being born. That was a genuine surprise, and it completely changes how we think about what these escaped black holes leave behind. And here's the part that really opens the door to something bigger. If a runaway supermassive black hole can happen once, it can absolutely happen again. Galaxy mergers aren't rare, exotic events. They happen all the time over the lifetime of a galaxy. Our own Milky Way has gone through multiple mergers in its past, and it's on course to collide with the Andromeda Galaxy billions of years from now. So black hole binary systems, where two supermassive black holes orbit each other, should form regularly. And wherever you have binary black holes, you have the conditions for either a full merger or a chaotic three-body gravitational interaction, both of which can send a black hole flying. For a long time, we thought of supermassive black holes as permanent fixtures, the immovable anchors sitting at the center of every large galaxy, going nowhere. But this discovery makes it clear that's simply not the case. They can be displaced, they can be ejected, they can go rogue. And even before Runaway Black Hole One was confirmed, astronomers had already spent years gathering evidence of other candidates. One particularly intriguing example is a spiral galaxy known by the rather unglamorous designation of J0437+2456, located around 228 million light-years from Earth. The black hole at its center has a mass of about 3 million times that of our Sun, and it appears to be moving at a noticeably different velocity compared to the rest of its host galaxy. That mismatch is a red flag. It suggests that black hole may not be sitting still at the galactic center where it belongs. Then there's another deeply puzzling case, the central galaxy in a cluster known as Abell 2261. By all calculations, this galaxy should be home to one of the most massive supermassive black holes in the entire observable universe, somewhere between 3 billion and 100 billion times the mass of our Sun. That is an almost incomprehensibly large object. And yet, when astronomers looked for it, it was simply gone, missing without a trace. A team of researchers is now investigating whether, similar to what happened with Runaway Black Hole One, this black hole was kicked out of the galaxy by gravitational recoil from a past merger event. If that's confirmed, it would be an extraordinary second data point in what might turn out to be a much more common phenomenon. These cases pile up and leave researchers with more questions than answers. How often are supermassive black holes actually flung from their galaxies? And how many of them are out there right now, wandering or rocketing through intergalactic space, completely undetected? We could be surrounded by these dark, invisible giants drifting through the void between galaxies, and we'd have no idea. Despite all the candidates, Runaway Black Hole One remains, at least for now, the only one we've actually been able to confirm. And even that was incredibly difficult to spot. It appeared as just a thin, faint, distant smear of light, easy to overlook, easy to dismiss. But that could be about to change in a big way. The Euclid mission and the Nancy Grace Roman Space Telescope are both designed to perform wide-field scans of the sky with clarity comparable to the Hubble Space Telescope, but covering vastly larger areas. And when you combine that kind of observational power with machine learning tools specifically trained to hunt for those long, faint streaks left by runaway black holes, the picture shifts dramatically. We could go from having just one confirmed case to discovering an entire population of known runaway supermassive black holes, the lone exception becoming a recognized category. One thing is already certain: galaxy collisions may stretch across billions of years, but they are anything but slow or peaceful. They are violent, chaotic, gravitationally catastrophic events, capable of launching entire supermassive black holes on runaway journeys across the cosmos. And perhaps the most beautiful irony in all of this is that the very same destructive forces tearing galaxies apart and hurling black holes into the void are also responsible for sparking the birth of millions of brand new stars in their wake.